Time to do the physics homework. Applying Newton's laws of motion. So let's see what we got here. For 45, got an elevator. Saw that coming. An elevator cab that weighs... Weight is the same as gravitational force. 27.8 thousand newtons. Is moving upward. What's the tension of the cable if the cab's speed is increasing at a rate of 1.22 meters per second squared and decreasing at a rate of 1.22 meters per second squared? All right, well, for part A, if it's going up and its speed is increasing, then the acceleration is upward. So that means the tension force here must be greater than this, must be winning, because the sum of all forces is equal to mass times acceleration. I'm sorry about that beeping noise coming from outside my classroom, like on the roof or something. Not really sure what's up with that. What's up with this, though, is the tension force. Get it? It's up with that. So this is the winning direction, so winners minus losers, that's my sum of all forces, is equal to mass times the acceleration here is 1.22, I believe. Okay, and the mass of this, I would have to divide this by 9.8, so 27,800 divided by 9.8 is about, let's call that 2840. Sticking with their 3 sig figs in this problem. That's 27,800. Okay, so looks like I'm going to have 2840 times 1.22 plus 27,800. So that tension in part A is going to be about 31,300 newtons. And I bet they're going to say 31.3 kilonewtons. That makes sense if the elevator is accelerating, not if it's going up. If it's going up at a constant velocity, then the tension would be exactly this. The forces would be balanced. But if it's accelerating upward, the tension has to be beating this to be changing the motion in that direction. So for part B, you might think, well, what's different in part B? Now the acceleration is the other direction. Of course, the force of gravity is the same, but the tension is backing off because it's slowing down. So that's going to switch the order of this. If you think about what's going to happen there, it just means that the tension force, instead of having to beat the gravitational force by this much, it's going to have to back off the gravitational force by that much to allow for that slowing down. So you can set up the equations and everything, but I know that it's going to be this minus this instead of this plus this. And okay, fine, I'll set up the equation. So this time, this is the winning direction. And if you're wondering, like, why are you not changing the sign of the acceleration here, Mr. McGrath? Because I'm orienting things, I'm setting up my equations based on what is the winning direction. I'm making the winning direction positive, so I don't ever have to put a negative here. Right? Acceleration is always going to be in the same direction as the winning direction, which is the direction of the sum of all forces. That's how I like to do it. So you can see here, if I move the t over here, and then I'm going to be subtracting that. So what's 27,800 minus 2840 times 1.22? That is going to be 24,300. They're probably going to say that because they reported kilonewtons in the original problem. All right, let me just check that here. 31.3, 24. Oh, yeah, nailed it. All right. So, what's next? 50. An even numbered problem. All right, so I've got 3 ballot boxes. Oh, that's apropos of election season. 3 ballot boxes are connected by cords, one of which wraps over a pulley having negligible friction. What's up with that negligible friction business? It just means you don't have to worry about anything happening. It means you can ignore any effects from the pulley, besides, of course, the redirect that it accomplishes. So there's A, B, and C. One of which wraps, and 3 masses are 30 kilograms, 40 kilograms, and 10 kilograms. When the assembly is released from rest, what's the tension in the cord connecting B and C? Okay, tension in the cord connecting B and C. I'm going to make force diagrams for each of the blocks, and so should you. If you didn't do that, pause this video right now and try to make those force diagrams. Okay, so that's going to be the force of gravity, 30G on that one. There's a supporting force here, and then there's a tension force. Now there's 2 different strings here, and they are separated by a mass. So those 2 tensions, this string and this string, do not have to have the same tension, for sure. If you want, if that seems weird to you, if you thought maybe they did, then consider this. Consider a string attached to the ceiling and a bowling ball here, and then there's another string and that's attached to a ping pong ball here. Do these tensions have to be the same? No. There's much more tension in this one than there is in this one. So, likewise here. How about block B? Well, block B, of course, it does have a gravitational force of 40G on it. Now there's 2 strings attached to this. This string will be pulling upward. I'm going to call this T1. That is the same string as this one. So that those tensions in the same string can't have different amounts of tension at the ends, only one tension. And it also has this T2 pulling down on it. And then this one has that, and then it has the T1. Is T1, or T2 rather, should I make T2 bigger, smaller, or equal to, or do I not know? Pause for a second, just make sure you understand how to deal with that question. When this is released from rest, it's definitely going, since there's no friction here, it's definitely going to start accelerating like this. So the force of gravity on this block must be the winning direction, because that's the direction of the acceleration. So I know for sure that T2 is less than that. I know that down is the winning direction for this, down is the winning direction for this, and right is the winning direction for this. Of course, there's only one force in that direction here. So, because those cancel each other out, no motion in that direction for block A. Okay, so what do I do here? We're going to see lots of problems like this in this section, in section 6, when we get to some rotational stuff later in chapters like 10, 11, 12. We're going to see more things like this. What you need to do here is set up a Newton's second law equation for each one of these blocks. Sum of all forces on block A is equal to mass times acceleration. Now the nice thing for us is the acceleration of the blocks is the same. It's the same quantity. Of course, these are going down and this is going to the side, but the magnitude of it, if I just treat this like the positive magnitude of the acceleration, it's the same. None of these strings are like stretching and changing lengths. So the distances between the blocks remains the same, therefore their motion is like locked together. So that's good. I think it's really important to write down those equations before you start plugging things in. Okay, so here, winners minus losers. There's only one winner here, no losers. Everybody gets a ribbon or a trophy. Here, got some losers. So winners minus losers, I got T2 and force of gravity here, 40G. So T2 plus 40G, that's the winning team. And then T1 is the loser. And then the mass of B is, oh, I meant to put the masses in there, sorry. So the mass of A is 30. Here the mass of B is 40 times A. Don't confuse the 40G with the mass. That's a gravitational force. The mass is just 40 kilograms. And here, winners, I've got the force of gravity, winning minus losing is equal to the mass of C times acceleration. Okay, now here's the magic thing that happens, and this happens every single time in problems of this type. If you take these three, I mean, you could do some substitutions, and I know you know how to do algebra, but here's the thing that's always going to work. If you add these three equations together, because the tensions are always going to be pulling in opposite directions on the objects, if you add the three equations together, the tensions will always cancel out. Nothing special about this time. And if you set up your equations so that all the forces are always on the left and the mass times acceleration is always on the right, then you are going to be laughing all the way to the bank, as they say. So the T1 minus T1, that cancels. T2 minus T2, that cancels. So what's left, I have 40G plus 10G. You can rewrite the equations like stacked up and add them if that's helpful for you. But I know all my T's are going to cancel out, plus minus T1 plus minus T2. So all that's left is 40G plus 10G. And then on the right-hand side, I got 30A, 40A, 10A. So my acceleration is 5/8 G. And you could leave it like that. I'm perfectly happy with that. Is that even what they're asking for? What's the tension? Nope. I guess we could use that for part B. The first thing they're asking is what's the tension in the cord connecting B and C? That's T2. So let's see. Once I know that, I could just plug that back in here. So I don't need to do that right now. I just need an equation with T2 in it. So T2 is equal to 10G minus 10A, which is 10 minus 50 over 8 times G, or however you want to simplify that. I'm getting, let's see, how many sig figs did they give us here? Oh, I guess I'll call that 36.8 newtons there. And that's part A. In part B, they would like to know how far does A move in the first 0.25 seconds. So how far does it move? We're getting talking about kinematics now. So let's see, my acceleration I know is 5/8 G, and the initial velocity is 0. I'd like to know how far it goes in the first 0.25 seconds. Good. So the VIT term is 0 here, so delta x is equal to 1/2 times the acceleration times the time squared. So let's see, that's 1/4 times 1/2 is 1/8 times that, so that's 5/64 of G. 5, I think. You can simplify that however you like, but I'm getting a delta x of 0.766 meters. And let me check that against my even answers. It looks like A is good and B is not correct. So what did I do there? Well, if I got A right, I must have the right acceleration. So what did I do here? I messed something up. Huh. How far does A move? So I'm not seeing it right off the bat here. I don't know. Why? Why are you not getting the right answer, McGrath? Let's see. There are occasionally wrong answers in the book. I'm not claiming that this is one of those cases, but I do not see anything that I am doing wrong here. And it definitely has, it's released from rest, right? I don't know. I don't think I like their answer. Oh, this is 1/4 already. So that's what I did, sorry. I tried to get too cute here and do the math in my head. So this is 1/4 squared, so it's 1/16th, so it's not, so I just need to take that answer divided by 4. There we go, sorry. Just bad arithmetic. 0.191 meters. All right, fixed, good. Now I'll sleep better tonight. 55. Math. Don't try to be a hero and do it without your calculator. That's the moral of that story. 2 blocks are in contact on a frictionless table. Why wouldn't they be? Like this. And let's see, what's the details? The mass of block 1 is 2.3 kilograms. The little one is 1.2 kilograms. And the force being applied to this one is 3.2 newtons. They want to know the magnitude of the force between the 2 blocks. Show that a force of the same magnitude of F is applied to the smaller block, but in the opposite direction. The magnitude of the force between the blocks is 2.1 newtons, which is not the same as calculated in first, and then explain the difference. Okay, so let's do this. First, this is just like the tension problem or the last problem in 50. We're going to do 2 force diagrams for block M1 and M2. So here, what are the forces acting on this block? Well, of course, I've got 2.3 G worth of gravitational force and that support force. And I've got this applied force. We're going to call it FP for force push. I'm calling it FA for force applied, 3.2 newtons. And then there's a block here, so that block, there's contact here, there's an interaction between those, and block B, or 2, is going to be pushing back on block A, but not as much as this, because they are going to accelerate forward from rest. So, force of B, or 2 on 1, let's say. That's the force of block 2 on block 1. And then here for mass 2, I've got 1.2 G worth of gravity, matching normal force. And what's pushing on that? It's not this force. This block doesn't know about that force. It just knows that this block is pushing on it. So this is the force of 1 on 2. And the force of 2 on 1 and the force of 1 on 2, that is a Newton's third law pair, right? That is that equal and opposite expression of this interaction between those two blocks. So those are equal but opposite in direction. And when we set up the equations, sum of all forces on 1 equal to the mass of 1 times the acceleration. Just like the last problem, the acceleration is the same. The blocks are going to move together. And when I set up this equation, this is that applied force, winner minus loser. And here I've got winner only. When I add them together, this is just like that tension force. Those are going to cancel out because that's a Newton's third law pair. Those are equal in magnitude, and I'm just dealing with magnitudes here. So Fa, those cancel, equals, I add those together, m1 plus m2 times A. Right. So A is equal to the applied force over m1 plus m2. And that is, let's see, what was the applied force? 3.2 divided by m1 plus m2, which is 3.5, which is an acceleration of 0.914. And that's not what they asked for. They asked for what is the interaction between them, what's this force. So I could multiply m2 by A here, and that is 1.2 times that, so about 1.1 newtons. And let me just check, make sure that that's good. Yep. And so for that next part, if you could go through and set up this whole thing again with the blocks, it'd be the other direction. But what's going to happen in the end is these equations are not really going to be different in the sense that when you add them together, you're going to get this expression again. The acceleration is going to be the same. And that makes sense. Whether you push on this, like when you're pushing on this, you don't really know that it's two blocks. It just feels like you're pushing, 3.5 kilograms worth of mass here. But the interaction force is going to be different because if you think about how this will play out, just like here, we multiplied the m2 by A to find this interaction force. If we were pushing from the other direction, we're going to multiply m1 by A, because the applied force would be on this block. So you can go through and set that up again, and also think about taking this to the extreme. What if it was like this? So think about if you're pushing this 1,001 kilograms worth of mass here, how much force is it going to require from this 1,000 kilogram mass to move this little one? This is going to be very small here. But on the other hand, if you're trying to push from this side, there's going to be an enormous amount of force here between those two. So that might help a little bit with the intuition there. Hey Finn?
What?
If you want to go down the hall, that bell was the time for that. I need to finish making this video. So you can, if you want to go, you should go. Let's see. What's next? Number 56. I think I'm probably not going to make it, buddy. Okay. Sorry about that. So here, constant force, this is really the same problem, isn't it? So if you had trouble with this one and you feel better about it now, then that's good. And you can blast through this one. You can try this one right now yourself. Maybe pause the video. So what do we have here? This applied force. Okay, so this time they're telling us the magnitude of the interblock force is 20 newtons. So that's what it is when the blocks are oriented this way. And then when they're oriented the other way, then the interblock force, it should be smaller, right, is A on B, B on A, it's the same. Newton's third law is now 10 newtons. Okay? And the blocks have a combined mass of 12 kilograms. Right? Okay. So we want to know what are the magnitudes of the acceleration and the applied force. Okay, so looking back, thinking about this problem, you can set up all those diagrams again, and I think actually we can't shortcut that. So here's block A, here's block B. This is for this situation here. So in this situation, I'm going to have sum of all forces on A equal to the mass of A times the acceleration of the blocks. On block A, I've got the applied force minus the interblock force. That would be B pushing back on A in that case, equal to mass of A times A. That's just like this. I'm not making the force diagrams again because they're identical to these. And the sum of all forces acting on B, that's the mass of B times its acceleration. And on B, I have the force of A on B. That's equal to that. So I know that the applied force is equal to, well, let's see. I do know that the same thing's going to happen here. Mass, the sum of the masses, which is 12 kilograms, times the acceleration. So there's a relation between the two quantities that we're supposed to find here. What's the applied force? What's the acceleration? So let's see if I can set that up for the other situation here, if I can do something productive with that. Or maybe, can I do it from here? Let's see. Let's see if I can get another equation over here when the blocks are set up the other way. So when it's like this, now I have, on block A, I have the, well, let's do B first, since it's coming first. The applied force minus the interblock force, and I know that that's 10, is equal to the mass of block A times the acceleration. And on block A, I have the interblock force of 10 newtons is equal to the mass of A times the acceleration. And here, I know that that's 20. So let's see what we can do here. I think it's just a matter of figuring out how to work the algebra here. So what if I added those two equations together? I think that would be a productive thing to do. If I add those together, I get 30 is equal to ma times acceleration and mb times acceleration. So that's ma plus mb times the acceleration. And I think we're home free now because that's 12. We know that the sum of the two masses is 12. So I get my accelerations 2.5 meters per second squared, and then if I multiply that by 12, I think that's 30. So those are the answers for those parts. That's a little kind of a funky problem. Our book likes those problems where you have to do system of equations kind of stuff. They think it's fun, cute, something like that. Probably a little funkier than what you're going to see on an assessment, I would guess. But a good problem, nonetheless. Especially good after you did 55. Have some reinforcement of that. Okay, 57, you got a block on a ramp. This is a classic, physics classic right here. And the old 30-degree angle. Got a block there. Another one hanging here. This is M1, which is 3.7 kilograms, and M2 is 2.3 kilograms. And we want to know what's the magnitude of the acceleration of each block, the direction, and the tension in the cord. Okay, well, this is a little tricky because it's hard to know if you release this. This is a heavier block, so if this was like 90 degrees, in other words, if they were just hanging over the pulley on either side, then this one would go down and this would go up. Now, it's not clear exactly what's going to happen because this one is heavier, but there's a ramp. I mean, if it was 0 degrees, then this one would go down. So I'm going to make an assumption. I'm going to assume that I know what the winning direction is. And if I'm wrong, then my acceleration will come out to be negative. Right? I'm going to assume that I know what the winning direction is. And if I do all my work based on that assumption and I get a negative value for the acceleration, it just means that I assumed wrong. And I don't have to redo it. I just need to switch the sign. Okay, so I'm going to assume that this is the winning direction, that they're going to accelerate this way. And I'm pretty confident about that assumption because I know that the sine of 30 degrees is a half, and I know that that's like the action direction here in terms of how much gravitational force. Well, the gravity down the ramp gravity is going to be the sine component of that, and that's going to be a half, and half of this is less than that. So that's what I'm basing my assumption on. But even if you just guessed, it's okay, and if you guess wrong, it's totally fine. You're just going to get a negative value in the end for the acceleration. So I need to make diagrams for M1 and M2. Good practice making a diagram for an object on a ramp. There's my ramp angle, there's my block, and there's gravity not caring about what the humans are doing, 3.7 g. And then I'm going to tilt that, drop my axis here, break up the gravitational force into those components. You can use a straight edge to do all this, if that helps you make it nice and neat. The support force is going to balance the cosine component of that. 30-degree angle will be up there at the top of the ramp. And then we're assuming that this is the winning direction, which means that the tension force is going to beat this. This is 3.7 g sine of 30, right there. Okay, so the sum of all forces on block 1 equal to mass of 1 times A. And the sum of all forces here, winner minus loser. Sine of 30 is 1/2. Sorry, I'm just going to write it out again. And then the mass of 1 times acceleration. The mass 2, this is the winning direction, so force of gravity, which is 2.3 G, is beating tension, and those are equal to each other because it's the same string. So sum of all forces on block 2 equal to mass of 2 times that acceleration. Winner minus loser. Okay, so we just need to add our equations together here. And just like will always happen, the t's are going to cancel out. And I'm going to get 2.3 G minus 1/2, that's the sine 30, times 3.7 G. That's what's on that side. And then on this side I have M1 plus M2 times A. That's 6A. So A is equal to 2.3 minus 3.7, half of that, times 9.8 divided by 6. How many sig figs were they using here? 3. So 0.735 meters per second squared. What are we being asked to find here? What's the magnitude of the acceleration, the direction of the acceleration of the hanging block? Down, we guessed right. And the tension in the cord. Let's see, where's the easiest place to do that? You could use either one of these equations to find the tension. I don't know, I don't think one's really easier than the other. Tension would be 2.3, I'm using this equation here, adding the tension there, subtracting this. So 2.3 G minus M2, which is 2.3 times the acceleration, 20.8 newtons. So let's just check that and see. Looks good. All right, how are we doing here? We have one more. Number 67. Okay, so this looks like it's, oh my goodness, there's 3 blocks. It's going to be so hard. It's not any harder. It's just going to have 3 equations instead of 2. But we should still be able to set it up exactly the same way. And just remember that there's 2 different chords here, so there's going to be 2 different tensions. All right. So everything's frictionless. What happens when the blocks are released? So let's make the force diagrams for A, B, and C. For A, when these are released, C is bigger, so everything's going to go this way. That's the winning direction. So on block A, I've got gravity, which block A is 6, is losing to tension 1. On block B, I've got gravity, which is that one 8G, balancing the normal force, and then T2 is going to be winning versus T1. And then on block C, I've got gravity 10G beating T2. So let's do it. Here, winners minus losers is T1 minus 6G. Here, winners minus losers. And here, winners minus losers. And add up the three equations. T1 is going to cancel out. T2s are going to cancel out. So it looks like I have 10G minus 6G, or 4G on that side. And then on this side I've got mass A, B, C, all times A. So A plus B plus C, the total mass is 24 times the acceleration. So it looks like the acceleration is going to be G over 6. And is that all we needed to find? They want to know what is the tension in the chord at the right. So that's T2. So that's going to come from this equation here. So T2 is 10G minus 10A. Just plugging in this to that equation and rearranging a little bit. So T2 is, let's see, 10, looks like 10 times 5/6 of G. Is that 81.7 newtons. And there you go. That problem had 3 dots next to it. Really, I mean, hardly. I hope you weren't intimidated by that. It's just the same as setting up all these. There's a whole lot going on in that assignment that's really, really important. Those are real important problems to understand how to do. The two-body problem, where you can add those equations together, and tensions, or when you have this kind, tensions are like inter-block interaction forces cancel out. That is big stuff. Of course, making force diagrams, including making them for things on ramps, super important skill. And you know what we're doing for the rest of this chapter? Just more practice. There's actually one assignment past this, and then a practicum, and then the test. But this is a good assignment to go back and practice stuff when you're getting ready for our test.